Okay, now let's consider polyprotic acid. Poly meaning many, protic meaning protons, so chemistry is very easy. Polyprotic, many proton acids. These are acids, compounds that can give up more than one proton, have two or more protons that can be given into solution to create more H+, thus making the solution more acidic. Here's an example, H2SO3 aqueous. Note that this is not H2SO4. H2SO4 is a strong acid, H2SO3 is a weak acid, but it'll dissociate in water to H plus and HSO3 minus with a Ka value of 1.6 times 10 to the minus second. I call this Ka1 because it's our first proton that leaves. However, this gives us HSO3 minus, which has a proton, so that proton might leave to form H plus aqueous plus SO3 2 minus aqueous. And the acid dissociation constant for that, Ka2, is 6.4 times 10 to the minus 8th. Note this is common. Note that the first dissociation, 10 to the minus second, the second 10 to the minus 8th, meaning this top reaction is going to produce more protons and water lies further to the right than this reaction does. And that is very easily explainable. There's a number of factors, the main one being that when you have H2SO3 as neutral, when you're trying to pull away H plus, you're trying to pull it away from something that's becoming HSO3 minus. You're trying to pull away something positive from something that's one negative. Down here, you're trying to pull something positive away from something that's 2 minus. It is much harder to pull a positive away from a 2 minus charge than a positive from a 1 minus charge. Good old Coulomb's law. All right. So not always, but most of the time, you're going to find out that the second ionization constant is quite a bit smaller than the first acid ion dissociation constant. All right. And we're also going to find out that the Ka from the first ionization is what determines the pH. That second Ka just isn't going to add very much H plus into solution. So let's take a look at this. Let's get really down and dirty and examine the math of why this statement is true, why the first ionization determines pH, not the second, or why the second really plays no role. Okay, here's our example right here. Question, what is the pH of 0.1 molar H2C6H6O6? Okay, looking up values, I find the first acid dissociation constant here, the second one here, and note this is times 10 to the minus 12th. And so, well, this is a weak acid. How do you know this is a weak acid, not a strong acid? Because we have the 6 common strong acid memorized. Run through them now in your head, if you will. The 6 strong acids. Okay, you should be done. Now, this is a weak acid, so if we want to know the pH, we need to know the H plus concentration. When this dissociates in water, if we need to know H plus concentration, we have to do ice tables for weak acids. So H2A plus H goes to H plus HA minus. I'm getting tired of writing such C6H6O6. Takes too long, so I'm just going to abbreviate this guy as A minus H as A. So H2A, initial change, equilibrium, draw the line, 0.1 molar, 0, 0, minus x plus x plus x, 0.1 minus x, x, and x. Have you seen this type of ice table before? Well, you've probably seen this one a lot, and you're going to see more of similar ones in the future. Very common, this type of ice table here. Plugging in our values, our first ionization constant, 8.0 times 10 to the minus 5th equals x squared over 0.1 minus x. Doing the math, we find x is 2.8 times 10 to the minus 3rd molar. And since that's our concentration of H plus at equilibrium, we could go from here and calculate pH, but I'm going to say, wait a minute here. I know you said up here that the first ionization determines pH. You don't have to worry about the second one, but let's worry about that second one. Let's actually do the math and see how much H plus is going to be added by the second ionization. What about the second ionization here? Well, let's look at this because something interesting to me is about to happen. The second ionization, HA minus, is in equilibrium with H plus plus A2 minus, but note our initial concentrations. At the end of this first ionization, we have this X and that X here. This 2.8 times 10 to the minus third molar is our concentration of H plus. That means that's X, which means the concentration of HA minus here is also 2.8 times 10 to the minus third molar. So these are our concentrations after the first ionization, but they are also our initial concentrations before the second ionization begins. You have to have that first ionization reaction up here before you can get the second one. So this X and this X are actually our initial concentrations for our second ionization. Our initial concentration of HA minus is X, 2.8 times 10 to the minus third. H plus is 2.8 times 10 to the minus third, and we have no A2 minus. The change, minus X plus X plus X. I drew it right quickly, that's an X. All right. So at equilibrium, we have 2.8 times 10 to the third minus X, 2.8 times 10 to the minus third plus X, and X. Putting it into our expression for Ka2, 1.6 times 10 to the minus 12th equals 2.8 times 10 to the minus third plus X times X over 2.8 times 10 to the minus third minus X. Can we get rid of the plus X and the minus X? Well, these 2.8 times 10 to the minus thirds are kind of small here, but look at this. 1.6 times 10 to the minus 12th. We know this reaction lies way, way, way to the left. We know this X is extremely, extremely small. So I'm going to say yes in this instance with this, such a small value for our Ka. We are going to ignore the plus X and the minus X. Can you see if we ignore the plus X and the minus X here, then our 2.8 times 10 to the minus third cancels this 2.8 times 10 to the minus third. Those two cancel, and we just get X equals 1.6 times 10 to the minus 12. All right. Well, what is this X? Is this our concentration of H plus? No. This X is not the concentration of H plus. The concentration of H plus is 2.8 times 10 to the minus third plus X. Our concentration of H plus is 2.8 times 10 to the negative third plus this 1.6 times 10 to the minus 12th. And just to show how ludicrous this is, I wrote it out long form. When I went back to elementary school, channeled my inner fifth grader, and noted that this works out to be 0.0028, 2.8 times 10 to the minus third, plus 0.00016. And you add it up and get 0.0028000000016. There's my answer for my concentration of H plus, but then I need to round it to 2 sig figs because 4 after the decimal place, it becomes 0.028. Can we see that our assumption here that this minus X and the plus X don't matter is absolutely true here? Adding this tiny bit to this 0.0028, it just doesn't matter whatsoever. And note, where did we get our original 0.0028 molarity for our concentration of H plus? We got that after just the first, up here. We got that after our first association. 2.8 times 10 to the minus third is our concentration of H plus. So this math here shows conclusively that the second ionization absolutely does not matter compared to the first ionization. And one of the main reasons it doesn't matter is something we're going to get into next chapter called the common ion effect, that when you start out with some product, I think we've seen this before, when you start out with some of your product already there, Le Chatelier says, well, if you already have some of the product, then this dissociation isn't going to happen nearly to the extent that it normally would, because some of this product is going to push the equilibrium a little further to the left than you'd expect it, making this plus X extremely small. It is much smaller than you'd expect due to normal dissociation because you already have some product to begin with. All right, so all this boils down to the pH of this way up here, 0.1 molar of this solution The pH is really only due to the first ionization, negative log of 0.0028. The pH is 2.55. All right, so here's a question for you. The pH of 1 molar H2SO4, what is it? Calculate that out. Note, if you're interested, the Ka for HSO4 minus, the Ka value for getting rid of this proton of HSO4 minus is 6.26 times 10 to the minus second. So then what is the pH of 0.1 molar H2SO4? Work that out. What did you get? Well, if you're using your brain, you should have come up with 0. Wait, pH equals 0? Does that mean it has no pH? 0.00? No, it doesn't mean there's no pH. Remember, pH means of 0 means it's very, very acidic. All right. Question. Did you get 0 here? If not, work it out again. And note, hopefully you didn't go through a whole bunch of math. If you went through a whole ton of math to get this, you were not thinking. So work it out. Try to get 0. If you can't get 0, that's the time to ask questions. All right. We will continue on with even more acids and bases in the next video.